Hi, folks. This is computing model. Part of the motivation or introduction to big data application analytics, describing the computing model. And the computing model is an intelligent cloud supporting an intelligent edge with a bunch of legacy databases and data repositories and so on, stored in the tens of zettabytes of data which we have gathered over the last few years. And the essential message is clouds are it. It looked very promising, and it's now become so promising that people no longer doubt it. They're absolutely dominant in industry. They're not so dominant in academia, but that's because academia is behind. So we give some overview of this, and we give some examples of how clouds are used, and we look towards the future. More details, especially of recent analyses, are given in the following lesson 6B. Thank you very much. Let's go for it. Thank you, 6A. That's not a very good thing. Well, never mind. Thank you. Okay, so this is a slight tangent, but it's still an interesting slide. It comes from this Tyobi.com's well-known site about programming language popularity. They have many more programming languages and lots of rich data. And it's sort of interesting how much these things vary. Look at this. When I actually last did it, both Java, I think it was here, Java and C++ and C were both getting creamed. Now Java and C are both rebounded. Java's a tiny bit ahead of C, but C is actually very popular because it's such a basic language. It can do lots of things if you're the Marine Corps and don't want to get a lot of help. And of course, the other important part is Python. Python is soaring. And C++ is important, but it's surprisingly that it lies so far below, say, C. Given academically, you would find in terms of instruction, C++ viewed as somewhat more important. And this is the order. C# is sort of probably disappearing, but because it really didn't quite make it. It's a nice language. I wrote quite a lot of C#. And JavaScript also is not such a great success. But anyway, it is amazing. Look, we have actually, over the last 20 years, Java has gone from 25% to maybe 16. C has gone from 20 to 16. It's really big changes, and the changes are pretty rapid. So that's sort of intriguing, and it's important, sort of worth thinking about. All right, so we will need lots of Here's an interesting chart from Gartner. discussing big data and cloud computing, as well as their hype curves. They have these priority matrices which plot transformational through moderate in terms of benefit against the time to realization. In 2012, I use this because it's the only one I have which has 5 different years on the same plot. 2012 media tablets, for example, were transformational in the near term. Big data and cloud computing was transformational in a 2 to 5 year period, and we have in later various variants of 3D printing. If you look at this chart, you see 3D printing is a dominant trend, and cloud computing and big data are also important trends. Except big data only popped in there in 2011 at the same place as cloud computing. Still there in 2012. Cloud computing is present in all 3 years, which is actually it's present forever, and which is slightly inconsistent with the 2 to 5 year timescale. Obviously, it took longer, or else it was so important it was incredibly transformational for many more years. I noticed Gartner has moved big data in 2013 to the 5 to 10 year slot. I have not seen this priority matrix for 2014. I mentioned you have to troll around the various blogs to pick up this nifty information from Gartner because it's not directly published. All right, a quick up-to-date survey of cloud service revenue, which is showing that it's continuing to go up by more than 50%. Here is the year-to-year change, and here is the 50% level. So it's been above 50% since 2015, and it's partly continuing that, although all these things slow down. If we look at the individual components, Amazon is totally dominant. Now it is still the leader, but Microsoft, which has done a great effort, and Google, which was surprisingly late, as they actually invented most of the concepts, but they didn't want to offer it as a public cloud. They wanted to offer it as their Google Compute platform, which was a clever thing. It was platform as a service, but special. So they suddenly realized that they'd made a mistake and corrected it. And they've advanced not substantially faster than Microsoft, faster than Amazon, but Microsoft has also gone up a comparable amount. So Google, Microsoft, and Amazon are the major players. This cloud service revenue is streaming up at an enormous rate, and it's an incredibly healthy field. And that's what the whole purpose, that's what underlies this whole course. All right, as we will see, public clouds have gone from disruptive to just what everybody uses. And soon you'll be criticized for not using them rather than for using them. And as I mentioned, they're becoming diverse. GPUs, FPGAs, high-speed networks, high-speed storage, lots of memory, little memory, so on. There's lots of software stacks. Software is all over the place. And there's the high-performance computing software stack, which is parallel computing oriented. It's less used because there's less parallel computing than big data computing. And the big data is dominated by what I call Apache software stack, which supports centralized and edge computing, streaming data, and batch data. And the big data, which will need hyperscale computing or high performance computing. And we'll have to have service-oriented architectures, which we'll discuss in these lectures. We will have to support the Internet of Things and edge computing. And the latter, edge computing, which is roughly the same as Internet of Things as far as we're concerned, will actually grow in importance. And you will find all communities fighting this out. Database, distributed computing, systems people, parallel computing, machine learning, computational science, data engineering, ... And they will investigate the same or similar ideas. They won't actually talk to each other much because they come from different universities or institutions, or they graduated at different times because some areas come and go. So anyway, The requirements are not very well explained by people because people just do things. They don't actually do what you're meant to do in systems engineering. Identify the requirements. Okay. All right, so this is a pretty simple slide. Comes from Business Intelligence, one of my favorite sources. And it basically discusses the three types of clouds. Public clouds, those are like Amazon, Google, Microsoft, IBM. One vendor sells to lots of different people. Private cloud, it's the same basic technology. Maybe it's OpenStack or even Docker these days. And it's just run for a particular owner, like, say, Walmart, and it's just an in-house collection of computers. Remember, Netflix uses a public cloud. Most probably large corporations use either the private cloud or more likely the hybrid strategy. Some private resources, and then you use public clouds that are bursting so that when you need more capability, you go to the public cloud. This allows you to minimize the expenditure on your private cloud, and then you can put the most secure, sensitive things in a private cloud. That assumes, probably incorrectly, that private clouds are less secure than public clouds. There was a later slide which points out that only 5% of security problems come from the cloud. 95% come from client events. All right, so here is security is rather different between these cases. Hybrid is typically you put, it's not actually harder security-wise because you tend to put different types of applications on the public and private versions. Public is very good for unpredictable demand because they have so many computers they can accommodate it. Private cloud is probably the most cost-effective if you use the best of cloud computing, but you optimize your private cloud for your needs. You have to run that cloud at something like 75% efficiency or utilization to match the pricing of Amazon, Google, and Microsoft. And here, of course, is hybrid is best if you need both. I told you why you need both. The public cloud can be used for bursting or unexpected business, which the private cloud only takes care of your regular stuff. And public clouds enabled a lot of the startups we see today because when back in 2000, when there were no such clouds, everybody brought their Sun microsystem servers to enable their information technology business. Now they just buy an account on Amazon, Microsoft, or Google. And of course, private and hybrids for people to have their own systems. If you're starting from scratch, I think today I would recommend, unless you have something really special, to go to a public cloud. Why bother to the effort having a data center, system admins, IT staff, and things? If you have an IT staff, you want to make it an IT staff that tells you how to run your applications, how to make a Hadoop and HBase work, and things like that. So obviously, this does not require the large number of support staff for private cloud needs. And the hybrid is possibly the hardest in that you have to not only run your private technology, but you have to know how to go to the public cloud and support it. All right, here is just, I put this in because it's sort of a picture of what a cloud technology looks like and how the software, the security, and the infrastructure looks. And this particular slide was meant to go from 1990, which is all first wave, basic Oracle database dominating the world, to now 2016, where Hadoop and Hive and Shark and things like that are giving Oracle a very serious run for their money. And I think Oracle, although it's still hugely popular, is not a very cost-effective technology. And here we have the software, visualization, business intelligence, memcache and things for caching, software for manipulating data. Here's the standard database transformation, ETL, extract, transform, and load. That's to get things in new forms. And here we're talking about a whole business in the third wave built around the computing. But here in the second wave is where you saw Hadoop and all sorts of other things. Why they choose EMC and Greenplum and NetApp and Netezza and Teradata, I wouldn't know. There are many other, huge numbers of other technologies and vendors here. I have this list which I showed actually probably earlier than this of the so-called Apache big data stack. It has over 350 software packages, so it's just enormously. And here it says big and fast. I'm not certain that's the right thing to say. It's really big, fast, and intelligent, because what's happened is we're in the current wave is we're adding much more data analytics, which it does actually put up here. And here we have more specialized applications, and we have more specialized security. So this is just pointing out that we've gone from a traditional data center to the first generation of clouds, to the second generation of clouds. And, well, there'll almost certainly be a fourth wave. Well, you can almost think deep learning is a dramatic impact because it runs on GPUs. And so it has very different infrastructure and issues than the types of database technologies which dominated the early use of these systems. Because even if they weren't Oracle databases, they were Hadoop plus Hive to mimic an Oracle database, or they were HBase to try to do a NoSQL version of a SQL database. So there were all sort of databases at some level with relatively modest analytics. Now the analytics is increasing in value. So now we have some somewhat older slides, and let's go on to those. Thank you. All right. What is a cloud? Well, it's a bunch of computers, 50,000 maybe, in one place. That place, the data center, is incredibly efficient because it's optimally designed, because it's so big, you can put a lot of effort into its design, and it's connected to the internet very fast because there are all these people typing their tweets away, and those tweets are rushing off to the cloud to be stored and spread out to the people's friends. And they were produced what used to be called Web 2.0. I don't think that term is used so much anymore because it's advanced so much, what you might call e-commerce or social networking or search, public-facing sites. But if you look at modern clouds, they're actually a little more like old clusters, which tended to be internally very high performance, not externally, because the traditional cluster did not have lots of people accessing it. So it had now the new high HPC cloud will have high performance networks, high performance CPU, ... And but always a cloud can be just thought of as the optimal giant data center connected very well to the internet. One can actually have public clouds, which are sitting there with everybody accessing them, or private clouds with the same technology, the same larger size, but they're focused on a large organization, your cereal manufacturing system, company, and so on. All right. Here is a little picture of the difference between clouds and traditional approaches. In clouds are elastic and on demand. And so this is shown in this graph here, contrasting a sort of traditional approach, server provisioning, to cloud provisioning. And we have this sort of load here, which is shown probably best here, goes up and down. And what you have here is here's this computers trying to track it, and you see they're not doing a very good job, and they are either under it or over it in this site here. Here they have too many computers. Here they're too few. But over here, the cloud is much more nimble and dynamic. It is bringing servers online dynamically. That's called elasticity. Elasticity is a key feature of modern clouds. So in this case here, you'll find the number of servers and the load, they essentially match. And that is meant to be how clouds are operated. And keep things comfortable, they actually are slightly over-provisioned most of the time. All right, here's a picture. This is some Google data center in Oregon, and it's larger than a football field. 10 times larger than a football field. That's what this shows here. Yeah, 10 times larger than a football field. And here we have a contrast of why clouds are cost effective. This is the component of the data center: storage, network administration, server systems administration. Here is the cost in a small and a large data center, and it's somewhere between 5 and 7 to 1. Not surprising. Efficiency of scale, that's a well-known feature of the world. And they use lots of power, but so they place it in a place like Columbia River, where there's hydroelectric power, which is relatively cheap and green. So you save money by large size, positioning with cheap power, and making certain you have great access to the internet. NIST produced a set of characteristic features of clouds. They have a large cloud working group. I actually was working on the big data working group, but there is also actually a better known cloud working group. So here we have on demand, elasticity. When your load goes up, the computers go up. We have shared resources, that's research pooling. We have this broad network access. Resource allocation is highly flexible, on demand. And also you pay for what you use, measured service. You don't, if I buy a cluster, I pay for that cluster whether or not I'm using it. And this has economies of scale, which we stressed in the last couple of slides, and economy of green features, because it uses the best, it can use the best possible power. We have these wonderful new software models we'll see, which powers concepts such as platform as a service, which is a value added to infrastructure as a service. The original clouds provided hardware on demand. You got out your credit card and purchased time on a piece of iron, a computer. But now you can purchase time on your platform, on your software, and you can see in front of you this wonderful GUI with all these software capabilities you can drag and drop in your program. And often, or typically, they're cheaper than the old approach, because the old approaches tend not to be used efficiently. All right, now we have a few slides on virtualization coming up, but virtualization has several features that are interesting. It's an abstraction, which means you run a job and it just runs. You don't know where it runs or what it runs on or things like that. All you know is it runs, and a little message runs up the internet to the job, and then it runs down the job to you, the results. Technically, virtualization means you use a hypervisor, which we'll discuss briefly, which support images. Images are a package, which is your software, possibly with the operating system included. And then you have a complete job, which is the image, which is either has the output thing added or is already built into the image, plus your own software, and you can save that image and rerun it. And then we efficiently pack lots of applications into one server. That's because we need to use all those cores. We don't want those cores idle, unless they really, if they ran, they would interfere with the operation of the other cores. We try to use as many cores as efficient. And so there will be interference. That means that the performance can be unreliable. It's not guaranteed. Whereas if you own your cluster, put your job on it, you know what you're going to get. And we need to be worried about security, and virtual machines have features in them which tend to make them more robust security than otherwise. Here's an old cloud use case. This was from the beginning of time when I first thought about clouds. It's a old Microsoft publication. They were looking at a data center which had 5,000 SQL servers running, and the CPUs are 9.75% utilized. That's because that's the old way of packaging was very inefficient. So you just repackaged everything as virtual machines and plunked down these images, and the images automatically relocated to idle cores. And you did the same computing with 6 times fewer servers because you were able to use multi jobs on the same server. And that's, of course, a lot of money saved. In this case here, you saved about $10 million a year. Pretty good. Here's an even more specific example from Google, a game from the past, where we were looking at Gmail compared to what we used to have. We used to run our own email server. Now, Gmail is actually better than my own email server, so I shouldn't run my own email server. But that wasn't true at the beginning of time when we were doing this. But also, a small email server is just much less efficient. And here's this thing showing us we increase the number of users. It gets more efficient to run. It costs less money. It's more green, and has less systems admin, less everything. It's just much better. Plus, the software is probably better. Gmail is difficult to compete with the modern software systems, Hotmail, Gmail, what have you. All right. Then, of course, there's elasticity, which means that, sort of was the beginning of clouds. Amazon noticed that they had a giant set of computers to run their e-commerce site, and they weren't always being used because you had to have enough computers to cope with Mother's Day, and so what do you do with those computers when it's not Mother's Day? So you rent those machines, and that was Amazon's incredibly brilliant and, in retrospect, simple idea. And as we will see, they actually make more money from renting their computers than using them. And then we had to use virtualization to efficiently use these computers doing packing and also to get good security. There were so many of these computers because Amazon's e-commerce operation was so big, and the future clouds were also built big, so you can get elasticity. If you have a small system, you can't really easily make it elastic. There's just not enough computers there to be elastic. And dynamically double the number of computers you're using on a job. And that assumes, which is true, that the hardware is actually quite cheap. People are what's expensive, and you can keep some of them in reserve. And I just note that 10% reserve on 100,000 servers, a couple of cloud data centers, is 10,000 servers, quite a lot spare. Exactly how you do this spareness and reserve and elasticity is a proprietary secret, whether you switch them off or have them in a low pass state, and whether they're loaded with software or not is not known. You actually probably do all of the above because you want a hierarchical system which switches on very, very quickly for some small jobs and switches on less quickly for large elastic changes. And this I mentioned already earlier, that some aspects of this field are difficult because they're locked in these giant companies which are making a huge amount of money, and they're not going to tell you how they do it. So, but anyway, I already mentioned these two states. If you switch them off, you can't switch them on very quickly, so you tend to probably have at least some of them in idle state but switched on. That is sort of the actually critical for the serverless computing model, which is meant to have these capabilities hidden, and then an event pumps in, which is function as a service, and invokes a function. That function is sitting there, sleeping away, and then bounds into action. Hi, folks. This is lesson 6B, the computing model second part. And even this second part has 3 subsections. Somewhat distinct. First subsection is an overall study of cloud computing mainly from Gartner, from different points of view, and these are all reasonably recent. The second study is all, these are all relatively recent. Second study is cloud market share, comparing the battle between Microsoft, Amazon, etc. And finally, we have some discussion about the hottest topic in the world, almost uh, blockchain, which is really revolutionizing enterprise work. So we have these three things: blockchain, cloud market share, and and the cloud computing model. And let's go. Thank you. All right, here we have the first part of lesson 6B, which is study that actually was done I did in 2017, so it's about a year old now, but it's still up to date till a year ago of aspects of cloud computing and the cloud computing model, mainly again coming from Gartner, which has these excellent studies. Okay, let's get started. Thank you. This is, of course, the Big Data Application Analytics course. All right, now we finally come to lesson 6B, which is actually pretty amusing. It's really amazing how much money is being spent on clouds. Tens of billions of dollars are being spent on cloud infrastructure every year. And part of this is clouds. So actually, maybe most of it is clouds that drive the internet companies, Facebook, Baidu, WeChat, Amazon, with their actual real business, but a lot of it is also public clouds, which are gaining more and more subscribers. It's a staggering development, and the scale is amazing. Let's see. Let's get some details on this. Okay, thank you. All right, big data application analytics, folks. This is lesson 6B, third part, blockchain. The blockchain is actually not a deep technology. It's been around in computer science for a long time, but it allows you to build very reliable, robust, secure ledgers. And so it's and also which ledgers are distributed. That's the key point. And we have a set of slides on that which now follow. This is the last discussion of the computing model. Thank you.